Hello, good people. In the previous video, we found the derivative value at x equals 2 for this function. We're going to do the derivative value of 1 for that same function, and we're going to do the same formula. I'm going to go a little bit faster, and I'm going to try to find a little bit more room. I'm going to do it on the side panel here. So we're going to say f prime of 1 is, oh, I'm sorry, my pen is not cooperating here. F prime of 1 is equal to the limit as h approaches 0 of, what's the formula? F of my x coordinate plus h minus f of my x coordinate, all divided by h. Now, what's this x coordinate? It's the x coordinate of the point, or in this case, this coordinate of the x coordinate of this point, the point of tangency, where I want to put my tangent line. Okay, same idea. We're going to take the limit as h approaches 0 of 1 plus h quantity squared minus 1 squared all over h. I'm going to have to square out the first term, and if you square out the first term, 1 squared is 1, plus h squared is h squared, plus I have to do the inside and the outside terms, the inner and outer, which means I have to multiply 1 times h and then double it. That's how I got that term. So all of that is part of the first square minus the second squared, which is 1, all divided over h. You should notice that just like before, in this numerator, this second term is going to cancel out with the first term. Or I should say the last term is going to cancel, just like it did over here, where we said this minus 4 and this positive 4 cancel out. Well, the same thing happens here. This minus 1 and this positive 1 cancel out. So I'm left with the limit as h approaches 0 of h squared plus 2h all over h. Once again, if I try to substitute a 0, that's not going to work. So I'm going to go ahead and factor out an h from the top. I'll be able to reduce the h. And now I can substitute the 0. And when I substitute the 0, I'm going to get 2. Great. So what do I win here? Well, I found the slope of the tangent line. The slope of the tangent line, the slope of this light blue tangent line is 2. And the slope of this purplish line is 4. What we're doing in this process is we're calculating the derivative value, the slope of the tangent line, the instantaneous rate of change at this point, x equals 1, by using the limit definition of the derivative. That's what this is called. The limit definition of the derivative. Using the difference quotient, we can figure that out. So I'm going to come over here, and I'm going to say, oh, this is 1. I'll use the color that I used to circle the original one, and that's just 1. So let's find this green one, but this time I'm going to use the other formula, because if you remember, the video said there were 2 limit definition formulas in order to find the derivative. So I'm going to use the other one, but you're going to see that we're still going to get the same answer. Not the same answer, but the same, we're going to get to what we need. I'm sorry. All right, so here's the last one, and I hope I don't run out of space here. So we're going to take the limit, but this time I'm not going to, no, you know what? I am going to use the h approaches 0, just to confirm that what we're doing works. This time it's going to be f of negative 2 plus h minus f of negative 2 all over h. Let's go a little bit faster. The limit as h approaches 0 of negative 2 plus h squared minus negative 2 squared. Now, why am I squaring? Because that's the function that we're using. If we were using a different function, well, then I would use that formula to figure things out, right? Keep going. The limit as h approaches 0 This is going to be negative 2 quantity squared is 4 plus h squared plus the product, the doubling of the product of these two. So multiply negative 2 times h and then double it, minus 4h, minus negative 2 squared is 4. And as you can see, just like before, this first and this last term cancel out. When I'm doing this limit definition, that should happen. So if something doesn't, if that cancellation doesn't happen, then you know you need to go back and check some things. So let's finish it. This will be the limit as h approaches 0. I noticed that out of my leftovers, both of them have an h, so I'm going to go ahead and factor out an h so that I can then cancel it, or reduce it, I'm sorry. And then when I substitute the 0, I'm going to get negative 4. I found the slope of the tangent line at this lime green tangent line. That would be negative 4. So what the sheet is telling us is that there's a pattern here, right? When x is 1, I'm sorry, this wasn't 1, this was 2. Some of you watching the video, maybe that clears things up a little bit. When my x value is 1, my slope value is 2. When my x value is 2, my slope value is 4. When my x value is negative 2, my slope value is negative 4. And so what we're seeing is there's a pattern between the slopes and my inputs. And that pattern is that for this particular function, x squared, to find the slope, all you need to do is double the x value. So if you double 1, hey, you get 2. If you double 2, you get 4. If you double negative 2, you get negative 4. And so this person that created, I did not create this, this person that created this form says, this is now a formula that we can use. And maybe I should say formula. This is the function that we can use for the derivative. But specifically, it has to be the derivative of x squared. If it was another function, then there would probably be another formula, another derivative function. But this rule will find the slope of the tangent line for any point on the parabola created by x squared. And that's kind of special because now we're moving from finding individual derivative values to finding a rule or a function that'll find the derivative value at any given x value just by plugging in the x coordinate. And so this is where we're headed. I'm going to pause the video. We'll come back. We'll do the bottom part of the page, and then we'll do some more examples.